Hey, hi guys. We are going to go through alkanes today. So last week, if you've gone through the introduction to organic chem, this is just a continuation. Alkanes is a fairly short chapter. It's very, very simple. So I hope that you can catch this fast. All right, so let's start. Alkanes, as you know from your Sec 3, Sec 4 work, they're generally not reactive, all right? A has strong CH and CC bonds and doesn't cleave easily. It is also non-polar, which makes it very unsusceptible to any form of electrophilic or nucleophilic attack. All right, so why is it non-polar? Okay, very simple, because the electronegativity of both C and H is about the same. All right, is around the same. So generally, we take alkanes as a non-polar compound. All right, so for alkanes, right, generally we are only going through two kinds of reaction. Number one is the combustion, and then the second one is our main dish for today, which is the free radical substitution. All right, for combustion, right, I'm pretty sure you have looked at this formula before. If you have not, it's okay. So I'm going to share with you how do you actually balance this equation. So when you start off with a CXHY kind of organic compound, right, a hydrocarbon, when you want to combust it, right, you basically add in the oxygen in excess, and then after it combusts, it will give you carbon dioxide plus water. So the thing here now is, how do we balance this equation if we do not yet know what is X and Y? All right, so very simple. The first thing you need to balance is the number of carbon, all right, which is I label it as 1. So this is the first thing. All right, so obviously the carbon all comes from the hydrocarbon, so you can just put an X here, because X number of atoms of carbon will come from this hydrocarbon. All right, and then the second one is your H, okay, because all of the H will come from the HY, right? So you literally have Y atoms of H on both sides. All right, since this is a H2, right, you will need to multiply it by Y over 2. All right, so that the 2 cancel out, you end up with Y atoms of H. Okay, then next, this is the most tricky part, and this is the last part, in fact. So your O, right, how do you balance it? How much oxygen do you need? You need X moles of oxygen to combine with the carbon dioxide. You also need Y over 4 amount of oxygen, because the 4 would cancel out to give you Y over 2 oxygen, which is actually the amount of oxygen that you literally need. Okay, so take note of the sequence, how you balance it. So even if you're faced with other formulas of organic compound, right, you can basically just make changes to this part, all right, to this part of the equation. All right, so that's the most important part. Okay, so with that, we will move on to our free radical substitution. Okay, so free radical substitution, right, is the only organic reaction that you learn for alkanes, of course, other than combustion. Okay, so let's look at the first example. When we have free radical sub, short for FRS, basically you put the alkanes, right, together with your halogen of your choice. All right, limited because we only want mono substitution. Okay, if you are putting excess, you basically get a poly substitution, okay, multi substitution. Okay, so you realize that I've actually circled these two things. All right, because the chlorine, right, you can see that the end result is it actually just substitute your hydrogen. All right, so they literally switch places. That's why we call it a substitution reaction. All right, so what are free radicals? Okay, they are highly reactive species, all right, with an unpaired electron formed by homolytic fission. Again, what is homolytic fission? Okay, so homolytic fission is the breaking of a covalent bond between two atoms such that each one only retain one of the shared electron. All right, so an example you can see is right here. All right, this is an example of homolytic fission. Homolytic means homo means same lah. Heterolytic, as I've shown you here, right? It means that both of the covalent bonds, right? Not both of the electrons in the covalent bond goes onto one of the atom. All right, so that atom will get a negative charge, and the one that didn't end up with any electron will be positively charged. All right, but that's not going to be part of what we're doing here. So what we're doing here is homolytic. So you end up with two chlorine radicals. Okay, so maybe because before we go further, right, this is our first functional group transformation, which we are going through. And basically in organic chem, right, when we do any reaction, right, our synthesis involves only two categories. Okay, number one is we change the functional group, and number two is we either cut short the carbon chain or lengthen it. All right, almost like 95% of the time we're going to be dealing with changing of functional group rather than altering the carbon chain. All right, so this is only like about 5% of the time. Okay, so let's continue with the free radical substitution mechanism. It has three main steps, which is initiation, propagation, and termination. Right, your initiation, as we've gone through earlier, is just to form your radical. All right, you can either use UV light or you can use heat. Okay, most of the time we'll try to go with UV light because that's the convention. Okay, step number two is propagation. All right, where once you have the alkanes, right, that you selected, your radical will abstract out the hydrogen. Means that you pull out a hydrogen atom with a lone electron. All right, so if you can visualize it, right, your alkanes, right, if you draw it out, CH, 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 CH. Okay, so what the chlorine actually does, right, is that it pulls out one of these guys to join with it. All right, so that leaves you with one of the bonding electron on carbon. All right, so theoretically speaking, it will be more correct to put the lone electron here rather than here. All right, and then subsequently, after that is done, right, the alkane becomes a radical, which will then go back and pull out a chlorine atom in the same way. All right, so now we regenerate this chlorine radical and we'll go back to step one again. Okay, so that's why the name is called propagation, right? So we will just keep on repeating these two steps again and again. Okay, then the last step, which will end the reaction, is where you have two radicals combining to form the product. All right, so you can actually just draw it in a skeletal manner. All right, like what we went through, right? So this is two carbon with a chloro substituent. And if you have basically two of the ethane, right, radical coming together to terminate, then you end up with butane. Okay, so do note that if chlorine is in excess, multi-substitution may occur. All right, if they were to ask you to show the mechanism, right, for a di-substituted halogenoalkane. So basically what will you do is you will take a mono-substituted alkane, all right, and you will use that as the reactant. So this is your first step, where you get the mono-substituted product, and then you simply take this product and use it as a reactant. So then at the end, you will end up with, all right, 2 dibrominated. So there's 2 bromines here being substituted in. All right, so the termination is actually the same. Okay, for termination step, we can either show all the available radical, or we can just pick any 2. All right, so we can combine these 2, we can combine these 2, and actually there's one more, right? 2 of the bromine coming together. But out of these 3 permutation, you just need to choose 2 as your termination steps. Okay, good enough. Okay, so let's look at a couple of work examples. Okay, when pentane reacts with chlorine, right, 3 different monochlorinated products are produced. Draw the structural formula of each of the 3 isomeric products and suggest with a reason which ratio they may be formed. Okay, for this type of question, right, you need to draw out your pentane and then ask yourself, okay, so how many different types of hydrogen there are? All right, so I've labeled for you in using colors and using alphabets, so you can see that there's actually 3 kinds of hydrogen. Okay, so substitution at any of the 6 HA, right, will give you 1 chloropentane. All right, as you can see here. So all of these 6 positions will yield you 1 chloropentane, the same product. Okay, likewise, if you substitute at HB, they will give you 2 chloropentane, and HC will give you 3 chloropentane. And the ratio that is formed is according to probability. All right, so this quick tip is basically just for you to think about it. In case you're not able to differentiate between HA, HB, and HC. All right, so a crude way will be actually if you ask yourself, if I got a substitution at this hydrogen, what will be my product form? All right, and remember the actual shape of this alkane, right, is actually 1, 2, 3, 4, 5, and these 3 hydrogen and these 3 hydrogen actually they are rotatable, they are all the same. All right, okay, so here actually is a test for you to check out. Okay, on your script, right, you shouldn't have the thing labeled so here you can see that I've actually labeled it in all the hydrogen using different color ink. All right, so you can just test yourself. For the first compound, you actually have 1, 2, 3, 4, 4 types of hydrogen. Second compound, you have 1, 2, 3, 4, 5 types of carbon. The third compound, you have 1, 2, 3, 4, 4 types of hydrogen. And the last compound, you have 1, 2, 3, just 3 kinds, because there's a plane, internal plane of symmetry. Okay, our last work example. All right, so if you have 2-methylpropane reacting with bromine to give you a mixture which the major product are the 2 monobrominated. Okay, what are the 2 factors which are responsible? Okay, so remember, there is basically 2 factors. If you're just looking at the probability, right, probability factor, then of course there is like you're just supposed to get 90% of the first kind and 10% of the second brominated alkane. But when we look at the actual numbers, right, the percentage doesn't tell us that, right? So why? Because of the stability of the radical. All right. So remember, in the free radical substitution, you actually have this intermediate, which is a radical. All right. So a radical is an electron deficient carbon atom. So when it's bonded to many R groups, right? And because R groups are electron donating, they will stabilize the electron deficient radical. All right, so this tertiary radical is actually the most stable. All right, followed by secondary, okay, quite stable, and primary is like not stable at all. All right, the worst is obviously is your methyl radical lah, which is like super not stable. Okay, so if you think about it, these two guys, all right, this radical will be what we call will form what we call the primary radical. All right, this will form what we call the tertiary radical. All right, that is why the product on the right tends to be more stable and more of it will form. All right, so this is the reason for the observed percentage. Okay, so the first reason is just the probability. That's the first factor. And the second factor is the stability of the radical. Okay. Okay, so with that, we have concluded the alkanes.